EDX Core Pure, Complex Numbers 1, Introduction. Terminology, real and imaginary parts, conjugate pairs. Consider the complex number z equals a plus bi, where a and b must be real numbers. The number has a real part, which is sometimes written as real z, and that would equal a. The number has an imaginary part, which can be written as imaginary z, and that would equal b. If we consider the same complex number z equals a plus bi, this number has what's called a conjugate pair, z star, where z star in this case would equal a minus bi, and again a and b need to be real. It's worth noting that the product z star will always be real, and we can demonstrate that so in doing z star, so that's a plus bi times a minus bi. So expand the brackets, there's an a squared, there's a plus abi, there's a minus abi, and there's a minus b squared I squared. Notice abi minus abi cancels out, and we're left with a squared. We know that I squared is minus 1, so minus b squared times I squared must be plus b squared. So z star will give you a real number. If we consider the equation a plus bi equals 7 minus 4i, then the equality of this equation implies that the real parts must be the same. So in this case, we're allowed to say that the real parts tell me that a must be exactly the same as 7. Likewise, the equality implies that the imaginary parts must be the same. So in this case, if we look at the imaginary parts, b must be exactly equal to minus 4. You do not include the I in the imaginary parts equation. So note that complex numbers are only equal if the real terms and the imaginary terms are each equal. So in effect, we get two requirements of equality, the real terms and then the imaginary terms. We can use the equality in division. A complex number equation is equivalent to having two separate equations. So we can talk about the real parts and the imaginary parts when it is convenient. This is particularly useful in division. So here, for example, we're trying to divide 3 minus 2i by 5 plus I, and we want the answer to be in the form a plus bi. So we could start off by cross multiplying to get 3 minus 2i is a plus bi times 5 plus I. Then if we expand the brackets, that's 5a, there's ai, 5bi, and bi squared. So 3 minus 2i is the same as 5i. bi squared is the same as b times minus 1, so that's minus b. And if you look at the imaginary part, we can take out I as a common factor. So now we have the real part, which I'll put a bracket round to make it stand out, and the imaginary part. So if we look at the real parts first, we have a 3 on the left hand side, we have 5a minus b on the right hand side, and due to the equality of these complex numbers, the real parts must match. I'll call that equation 1. If we now look at the imaginary parts, there's a minus 2 on the left hand side, there's a plus 5b on the right hand side, and those imaginary parts must match as well. And if we solve these equations simultaneously, we will find that a has to be exactly 1/2 and b has to be exactly minus 1/2. So there we see how we've expanded the brackets and collected like terms. And if we look at the real parts and the imaginary parts, we get simultaneous equations which can be solved for A and then for B. So we can use this idea to solve a more complicated equation. So here we're looking for Z, and we're told that it is x plus yi. And we want to find the values of x plus y such that z plus 3i z star is exactly the same as minus 1 plus 13i. Z star is the conjugate of z. So the first thing to note is if z star is a conjugate of z, then z star can be written as x minus yi. So if we substitute our complex numbers z and z star, the equation becomes z, which is x plus yi plus 3i times z star, which is x minus yi, and equals minus 1 plus 13i. So we've got x plus yi plus, and now I'm going to expand the brackets, so we've got 3i times x, so that's 3xi, minus 3yi squared is minus 1 plus 13i. If we look at this term first, I squared is minus 1, so this term becomes minus 3i times minus 1, which is plus 3y. So we've got an x, we've got plus 3y, and we've got yi plus 3xi for the imaginary parts equals minus 1 plus 13i. So we've got x plus 3i, which is the real part, and if I take out a common factor of I, we've got y plus 3x, the imaginary part, times I is the same as minus 1 plus 13i. Because we have equality of complex numbers, we can now pull out the real part. So the real part on the left hand side is x plus 3y, and the real part on the right hand side is minus 1. I'll call that equation 1. And if you look at the imaginary parts now, we've got y plus 3x on the left hand side is imaginary, 13 on the right hand side, and they must match, so they can put equals there. I can now solve these simultaneously by doing 3 times equation 1 and taking away equation 2, which will give me 8y is minus 16, so y must be minus 2, and if I substitute back into one of the equations, I'll end up with x equals 5. So the real part is 5, the imaginary part is minus 2, and therefore z can be written as 5 minus 2i. That's the original complex number in the equation. So in the next session we will be looking at linking complex numbers to quadratic equations.